Let's go through the answers to homework number 7, the assignment that you turned in last week that I just finished grading today. I thought you needed more practice with writing equilibrium constants, so this first problem here is giving you a bunch of reactions. And everybody did pretty well on this. It's always products over reactants, so here's the first one, N2O over, or times NO2 over NO to the third power. So notice, if you see all gases are aqueous, they have to go into the equilibrium expression. These seem pretty straightforward. The equilibrium of a weak acid, hydrofluoric acid, the equilibrium expression is the concentration of H plus times fluoride ion over HF. They're all aqueous, so they have to appear. The third one, 3 moles of oxygen. So oxygen to the third power is the product divided by ozone's concentration to the second power is the correct answer. I asked you some questions about Le Chatelier's principle here. If you increase the pressure on this equilibrium, which way does it shift? It's going to shift in the direction that produces fewer moles of gas, so it would shift to the left because there's only 2 moles of gas on the left, 3 on the right, so it's going to shift that way. Raising the temperature, well, heat's on the right, it's exothermic, so raising the temperature is like adding a product, so it shifts to the left. Removing oxygen as it forms causes this equilibrium to shift to the right. If you remove a product, the equilibrium is going to move to the right or shift to the right to compensate for what you're removing to make the forward reaction go faster, so it shifts to the right. This one, N2O4 gas, decomposing to 2 NO2 gas molecules, NO2 squared over N2O4. So remember, you must write everything with a bracket to indicate that it's moles per liter. Now, there is a different way to write an equilibrium constant expression for gases. You can use the pressure as well, but we didn't really discuss that. Expressing the gas concentration as moles per liter is totally fine as well. This one, you can't put water in the equilibrium expression because it's a pure liquid. Pure liquids and solids do not appear as I've told you in these videos, because the concentration of water can't change. Only substances whose concentrations can change go into this expression. So it's the concentration of carbon monoxide divided by the concentration of CO2 times the concentration of H2 is the proper answer. This number 2 problem, you got 2 moles of SO2 gas reacting with oxygen to give you 2 moles of SO3. It's got a very large equilibrium constant. It means it favors the products. If K is much larger than 1, the equilibrium lies far to the left. If the equilibrium constant is much smaller than 1, the equilibrium lies to the left. Like this would have a very small equilibrium constant because it's a weak acid. So this equilibrium would lie far to the left. The equilibrium constant for this would be somewhere around 10 to the negative 5th power, a very, very tiny number. Second page, number 3. This was, most people got this one right. This is what's called a combined gas law problem. You had to use this equation. P1V1 over T1 equals P2V2 over T2. You're solving for V2. So for these, I recommend you solve it in general and then plug everything in. I wanted you to show it like this with all the units. Notice I didn't have to convert milliliters to liters. I had to have temperatures in Kelvin, and the pressures were given in atmospheres. So you just had to kind of pay attention to notice that these conditions here were the initial conditions, and the second subscript 2 conditions were the higher temperature and higher pressure. So the bubble would actually expand to 14 milliliters. Number 4, most people seem to get this right. It was good to see. You burn octane with a lot of oxygen, you get a lot of water and a lot of CO2. I asked how much CO2 would you get if let's say you just assumed you burned the entire tank of gas. Let's say it's 12 gallons. I figured that out to be about 33,000 grams of octane. So how much CO2 would you get? So take 33,000 grams of octane, convert it to moles. You get about 290 moles. Now, I rounded off as I went. Some people didn't. You didn't have to. But as long as you round off to 2 sig figs at the end, that's fine. It's actually better to carry through all the extra digits until the end, so you don't get what's called round-off error. But either way is fine. 33,000 grams is about 290 moles of octane. It's a 16 to 2 ratio, so you got to multiply 290 moles of octane times 16 over 2 to get about 2,300 moles of CO2, and then plug that in to the ideal gas law where V equals nRT over P. Here's your moles N, R, T is 25 degrees C expressed as Kelvin, 298 Kelvin, divided by 1 atmosphere. I get about 56,000 liters. You would expect a very large volume of gas because, you know, it's a lot of gasoline being burned, and the gas that we generate is always a much larger volume than you think. So 56,000 liters. Some people thought this was STP, which I can understand, but STP is 1 atmosphere and 0 degrees C. So you couldn't use that assumption that this meant that the volume was 22.4 liters per mole. You can't do that. Number 5, I asked you about, based on intermolecular forces, circle the formula of the compound in each pair that has the higher boiling point. So in this pair, you're comparing an alcohol with a similar sized hydrocarbon. The alcohol is always going to have the higher boiling point because it's got the ability to hydrogen bond to itself. It takes more energy to strip or to remove butanol molecules from each other. Higher boiling point. This is an ionic compound versus water. Water, as you know, boils at 100 degrees C. Salt, the boiling point, many hundreds of degrees, maybe a couple thousand degrees, I'm not sure. So ionic compounds will always have higher boiling points than a covalent compound. And here it was a little tricky. Nitrogen gas and oxygen gas. Well, the heavier one would have the higher boiling point. That's 28 grams per mole. That's 32 grams per mole. So oxygen's the right answer. Both the boiling points are many, many degrees below 0, but oxygen is a little less negative, so that means it's a higher boiling point. Number 6, I asked, why does table salt dissolve better in water than in gasoline? Use intermolecular forces in your explanation. Pretty simple answer. You could just say, you know, like dissolves like, right? Polar things dissolve polar things best, and nonpolar things dissolve nonpolar things best. So sodium chloride's polar, so it dissolves well in water, which is also polar. The intermolecular forces between sodium chloride and gasoline are too weak for them to interact. There's really no reason for gasoline molecules to interact with sodium chloride. They're happy together, and so are sodium chloride, so there's not enough of an attraction for them to mix. State one example of each of the types of solutions. A gas-gas mixture, air, filtered air is most people said air. Solid-solid, brass, bronze, tooth fillings, which is a mixture of silver and mercury. Solid liquid, some people said mercury filling, so I said that was fine too. I'm not sure what the solid is, but the liquid, mercury is a liquid at room temperature. So maybe my suggestion here wasn't totally right, I guess, but mercury and silver mixed together do make a solid. So solid and liquid is salty water or coffee or tap water. There's many, many examples of that. A liquid-liquid mixture, I wanted you to specify a solution that had at least 2 components. So gasoline made up of many components, wine, some people just said mixed drinks, a lot of alcohol involved. So, briefly define the following terms. A saturated solution is a solution that contains the maximum amount of solute dissolved in a given amount of solvent. I wanted you to say something about maximum amount of solute dissolved in something. I wanted you to say the word solvent. There's often excess solute as a solid at the bottom of the container. I didn't necessarily need to see that, but that's really what you have when you have a saturated solution. You've dumped in so much solid that not all of it dissolves, so it's saturated. Unsaturated just means you have less than the maximum amount of solute dissolved in a given amount of solvent. I wanted to see both words, solute and solvent. Are most solids more or less soluble at high temperature? They're more soluble, as you know, like sugar dissolves better in hot water. What else? Salt dissolves better in hot water. Most things dissolve better in hot water. I'm sure we could find a few exceptions if we thought long about it, but the general trend is what I just said. Let's see, I think I've covered everything on that page. Number 10, isotonic saline is a dilute solution of salt, NaCl in water. What's the molarity of this solution if you take 8.77 grams and dissolve it in 1,000 milliliters, which is a liter? This was pretty simple. You just take 8.77 grams, convert it to moles, so divide by the molar mass of NaCl, 58.44 grams. You get moles on top divided by liters. You could do it all in one step. You get 0.150 molar to the 3 significant figures, because this is going to limit the precision of your answer. Fill in the blanks. This one got a lot of people, for some reason, I think they just assume that the water is always the solvent, but the solvent in a solution is the material or the substance that's present in the larger amount. So 70% volume to volume percent means milliliters over milliliters. So whatever is present in the larger amount volume-wise is the solvent. 70% means it's 70% alcohol and 30% water. So alcohol, isopropyl alcohol is the solvent, water is the solute. And so you just had to take 0.7 as a decimal, 0.7 times 500, and you get 350 milliliters of the solution is isopropyl alcohol, and the remainder 150 is water. So they would have to add up to give you 500 mils. I don't think that gave most people too much trouble. They might have mixed up some of these, but you had all the numbers right, which is good. You just mixed up the concept a little bit. No big deal. This problem here, number 12, concentrated nitric acid has a density of 1.41 grams, 70% by mass. You didn't even need those. I told you the molarity is 15.7 moles per liter. If you take 50 mils of this concentrated solution and dilute it to 500 mils with water, so that's a dilution factor of 10. Here it is, 1 over 10. 50 over 500 is cutting 15.7 by a factor of 10, so just divide 15.7 by 10, you get 1.57 molar. The molarity of a diluted solution is always going to be less than the molarity of the concentrated solution. That's why we say this is concentrated, that's dilute. So that didn't seem to give too many people any problems. That's good. This one you didn't need to show me any work. It was just a fill in the blank. If you did show work, that was fine. Good practice for you. But to cut the molarity in half, you would just have to add an equal amount of water to acid, 100 to 100, because you'd get 100 out of 200, which is a dilution factor of 1/2 to cut the molarity in half. And then the last one was a colligative property problem. Colligative properties depend on the number of particles. So when you dissolve something in water or some solvent, you're going to raise the boiling point of the resulting solution, and you're also going to lower the freezing point. So I asked you about which order these in order of decreasing boiling point. So you had to list the highest boiling point over here and the lowest boiling point over here. The highest boiling point is going to be the one with the most particles. So you'd have to say, okay, well, glucose is a molecular compound. It doesn't dissociate. So 0.15 moles of glucose give you 0.15 moles of particles. 0.040 moles per liter of aluminum nitrate gives you, well, aluminum nitrate breaks up into 4 molecules, an aluminum ion and 3 nitrates. So 4 times 0.04 is 0.16 moles of particles. So that's higher than glucose. That's why aluminum nitrate is before glucose, because it's a higher boiling point. 0.10 molar NaCl would dissociate into 2 particles, a sodium ion and a chloride ion. So you'd actually get 0.2 moles, which is the highest number. That's why this solution has the highest boiling point, followed by aluminum nitrate, which has 0.16 moles of particles. Remember, I'm just taking the number of ions times the molarity to get how many particles to figure out how to order these. And then the last 2 that remained were covalent compounds, molecular compounds that don't dissociate. So the one that has the higher concentration is going to have the higher boiling point. So this is the correct answer from high to low. All right, keep going. You guys are doing a good job, and we'll see you in the next video. I'm still working on that buffers lab, but I'll have it ready in hopefully a day or 2.